My job is to introduce the next speaker. Is Professor Anastasopoulos, and he is going to talk about incentive design, and I'll let him talk about his topic, but then I will introduce him in terms of his background. Achilles received a diploma in electrical engineering from National Technical University of Athens, Greece, in 1993, the master and PhD degree in electrical engineering from USC in 1994 and 1999, respectively. I think he's a student of Dr. Andreas Polydorosis. He's currently an associate professor at the University of Michigan, Ann Arbor, Department of WE and CS. His research interest lies in the general area of communication theory, with an emphasis in channel coding, multi-user channels, as well as connections between multi-user communications and decentralized stochastic control. He is the co-author of the book named Iterative Detection, Adaptive Complexity Reduction, and Applications. That was published in the year 2001. Dr. Anastasopoulos is the recipient of the Myronis Fellowship in 1996 from graduate school at USC, and he is the recipient of the National Science Foundation Career Award back in 2004. He served as a technical program committee member for ICC 2003, GlobeCon 2004, and 2012, and as well as the editorial board of the IEEE Transaction on Communications. So without further ado, I'll let Achilles speak.
Thank you very much.
Here's pointer spread barely working.
Thank you all. I'm very glad to be here. I was here from 93 to 99. Since then, only been once back, so I feel a bit guilty that I haven't been here as much as I wanted to, or I could. But it's really nice to be here, and I see all these familiar faces. Some of you are familiar, but I cannot place them exactly in space and time. But hopefully by tomorrow, I will talk to all of you, and we'll be able to share memories and jokes of the past and so on. So this is a presentation that I joint work with my graduate student Dipanshu Vasal. Let me first apologize for the maize and blue University of Michigan color theme. I was talking to some people earlier. If this is any consolation, I haven't been to a football game the 13 years that I've been in Ann Arbor, so I'm a true Trojan at heart. What I want to talk about today is cooperative communications and how to provide incentives to achieve certain goals in cooperative communications. And when I talk about cooperative communications, the prototypical example that comes to mind is a relay channel, a simple relay channel, where you have a source and a destination. The source wants to transmit some information to the destination, but for some reason, this transmission is costly to do it directly. And so there is a presence of a relay that is willing to help in that transmission by relaying the information. And hopefully this is done in a more efficient way. And that's the basic idea. When we talk about a relay, you can think of your laptop, or you can think of your tablet, and even you can think of your smartphone. I was talking to some people from Qualcomm here, and please let me know if this is not correct, but they're seriously considering direct communication from mobile to mobile in the cellular band. So even your smartphone can act as a relay in the cellular transmission. So whenever we have a problem like that, I suppose we want to find its salient features. So what are the salient features of this problem? First of all, we have multiple agents. And whenever you have multiple agents, you have to ask, what do these agents know about the system. So they can either know everything about the system, or the channel gains, the backlog information, the state of the system, and so on, or they have some partial information, a more practical scenario, apparently. Also, when you have multiple agents, you have to worry about whether these agents act as a team, having a common goal in mind that they want to pursue, or they act in a selfish manner, having individual goals in mind. Of course, they act strategically when they are selfish. Also, this system is not a one-shot communication system. It involves, as we said, these multiple agents who observe the system partially, try to act upon their observations, try to partially control it, get some feedback about their control that they did, and so on and so forth. So we have a dynamic evolution of a stochastic system. Okay. And so all in all, what this means is that we have a very intimate interaction between communication, control, and incentive compatibility. And I want to build on a theme that Ubli talked about in her talk. I don't have sensing here, but you can easily add sensing in this nice mix of these different disciplines. And this is really what makes these classes of problems interesting and very challenging. So we're faced with this prototypical example of cooperative communication, and already we have so many details to worry about. So one thing we can do is to find an abstraction of this problem, the simplest possible version of this, come up with a mathematical model, and try to formulate a problem. Okay? So here is my abstract model that I want to talk about. As we said, we have a source and a relay, two agents in the system. They are equipped with their own queues. They receive their own traffics, which you can model in the simplest possible way as Bernoulli arrivals with probabilities P and Q. And they have, let's suppose that the time is discrete, so everything is packetized here. The size of the queues, the state of the queues can be denoted by xt1 and xt2 and so on. And they have available actions at each time instance. So the actions of the source is either to transmit directly a packet to the destination, spending some energy, E13, or transmit through the relay, spending some energy, E12, or do nothing, not transmit anything. And similarly, the relay can either do nothing and accept a packet from the source, or do nothing and reject a packet from the source, or take a packet from its queue and transmit it to the destination, spending some energy, E23. And let's assume a very simple, the simplest possible collision model. If two packets are transmitted simultaneously, they collide, and if one packet is transmitted, it goes through. So really, I'm interested not in the physical layer aspect of this problem, but more on the Mach layer aspect and the cooperation aspect of this problem. And further, maybe we can assume that we have some optional feedback, so we receive some acknowledgement or not whether, what happened in the channel. And this is broadcasted back to the users. So in a problem like that, you want to see what is the tension between the two users. And the tension comes because if you don't transmit anything and wait, then packets will accumulate in your queue. And if you start transmitting, then you will spend a lot of energy. Okay? And so to quantify that, we assume that we have some cost function, instantaneous cost function. At every time t, users pay some cost. That depends on the state of their queue. This is a proxy of the delay that incurs in the packet. And the action that they take, this is a proxy of the energy that they spend. And to finish up with this model, we can have some very reasonable assumptions. We can assume that the total energy of transmitting a packet through the relay and from the relay to the destination is definitely smaller than a direct transmission. Otherwise, it wouldn't make any sense to have relaying. And also that the total traffic can be serviced, and so it doesn't accumulate in the queues of the two users. Okay, so this is the simple mathematical model of the problem. Now, with this model, I want to describe two different scenarios, two different problem formulations with increasing degree of difficulty. So the first problem is a centralized version of the problem, whereby you have a central controller that knows everything about the system, the two queue sizes, let's say, and dictates certain actions to the two users. And we will assume that the users will obey the central controller. The actions can be functions of the entire history of everything that has been observed and everything that has been done in the system. Okay? So the question is, let's find this set of policies, this set of functions, to minimize the total cost both the cost of user 1 and user 2, averaged over the entire time horizon t. So as you can see here, the dictator, let's say the centralized controller, is interested in the social, optimizing the overall behavior of the system. Okay? It turns out that this is a very simple problem. It's what is called the centralized stochastic control problem. You can easily show that xt is essentially a Markov decision process, and thus it can be solved in a standardized fashion using dynamic programming. And from this theory, you can easily also see that the actions can only be functions, need only be functions of the current states x1t and x2t, so you can drop the entire rest of the history and everything else. So really, we have a very simple solution here. And if you go a little bit in depth in the actual characterization of these functions, you will see that under very mild assumptions, the protocol that emerges makes a lot of sense. So really, the protocol is the following. Give always priority to the relay. Whenever the relay has something to transmit, let them transmit, and the transmitter should be silent. And whenever the relay doesn't have anything to transmit, then it should accept a packet from the source. So the second scenario is the more interesting one. What happens if each user, the two agents that we have in this problem, the source and the relay, act selfishly? In this case, they want to minimize only their own cost, of course, summed over the entire horizon and averaged over the statistics of the system. And in this case, we are in the regime, I suppose, of game theory. The two users can play some actions, can have some strategies. These affect both their costs, so they have to find a way to get to the best possible result under the assumption of rationality. So one can study this game, and usually when we study games, we study the equilibrium of these games. And the unfortunate thing is that when you study the equilibrium of that game, you see that the equilibrium solutions do not coincide with the centralized problem that I talked about in scenario A. And sometimes this is called the price of anarchy. For example, you can easily see that under no circumstances the relay would want to accept any packet. Okay? It would rather reject it, and because if it accepts it, it will stay in his queue, it will add up to his own cost, and it will have to spend energy to transmit it as well. Okay? Although this might be beneficial to the whole society, let's say to the whole system. So to see it in a slightly different way, when you talk about an optimization of a system goal, then you have to find this green solution, F star, that minimizes the sum of the costs. While when you talk about an equilibrium, this is the concept of this saddle point solution where each user cannot deviate, doesn't want to deviate if the other user sticks with the equilibrium solution. Okay? So in the next slide, I want to show you that there's a very trivial mechanism that can make F star, that is the solution of the optimal problem, of the centralized problem, a Nash equilibrium of the game we're discussing. Okay, but there will be problems. So let's start with this very simple solution. So the solution is to pay a certain amount of money, a certain amount of credit. The source pays the relay a certain amount of credit, equal to some linear combination of the two costs of the two users, J2 and J1. Okay? So what happens then? The resulting costs of the two users are different now. User 1 increases its cost by plus m. User 2 decreases its cost by minus m. But all in all, you see that the overall cost, the induced cost, equals to some fraction of the total cost of the system. And thus, my individual goal, if I am user 1, is aligned to the social goal here. And same for user 2. And it's easy to see now that the optimal solution F star of the centralized system is indeed also a Nash equilibrium. What's the catch? Oh, before I get to that. Also, you can see that we have here a situation where we have balanced budget. This means that in the end of this process, there won't be any need for money coming into that system, or there won't be any money left in the pot to be distributed somehow. Okay? So what's the catch with this approach? The catch is that by doing that, you're introducing more and more equilibria into that system. And maybe that equilibria of that game have nothing to do with the original solution F star, that is the optimal solution that you want to achieve. And whenever you have a game with multiple equilibria, there is always a question. What will the agents do? They cannot prefer one over the other. Okay? So really the question for the designer is, how can we design some kind of a mechanism where we give incentives to users? And this mechanism seems pretty simple. That is a mechanism whereby the relay pays, or the source pays the relay some amount of money, so that there's always only one equilibrium in the induced game, and that equilibrium coincides with the central solution. Okay? So this is the kind of question that we wanted to answer. And we answered it in the positive. We define a function, a payment function m of t, which depends on the time instance t in this finite horizon problem. It depends on the state that the users are at time t and on the actions that they take. Now, under this assumption, and the assumptions that I mentioned for the original problem, and under the additional assumption that the users know and the mechanism designer knows exactly the shape of the cost functions, and under the additional assumption that the two users also know the states x1t and x2t, you can show that indeed you can find such a function, and indeed this function induces a single equilibrium in the game, and that single equilibrium coincides with a centralized solution. And since we're talking about dynamic games here, the more appropriate concept of equilibrium is not the Nash equilibrium, but a subgame perfect one, but this is sort of a detail here. I know that I have plenty of time, so I will just try to give you an idea of how this thing works. Okay, so how do you go about designing this transfer of money? So the idea behind the proof is a backward inductive one. So we will actually design this, construct these transfers by starting at time capital T and going backwards. So imagine that you are at some particular time t, and the system is at some state x of t. Now the designer is faced with a single shot problem. What is this single shot problem? What will the users do at that particular time t? The cost that will incur at that time t is nothing else but what is called the cost to go functions from that time t on. That is, on the average, what we expect that they will have to pay from that time on. Now, since I have designed this problem in a backward recursive fashion, I already know these costs. So I am faced as a designer with this very simple one-shot strategic game. And we have this intermediate result, as a parenthesis, that for any given single-shot strategic game, if you pick any pair of actions, let's say A star, B star, you can always find a transfer of money from one user to the other. So you can make that particular action a dominant strategy equilibrium. And for those of you who have seen some of the equilibria concepts, you realize that strictly dominance is a very strict concept in game theory. It means that no matter what the other player plays, you should play strategy A star. And whatever the other player wants to play, you should always play B star, and so on. Unfortunately, this very strict concept cannot translate to the dynamic game. But that's not what we want. It turns out that this strong concept in the instantaneous game can translate to a single, unique Nash or subgame perfect equilibrium in the dynamic game. And that essentially concludes the proof. So, to conclude my talk, we're interested in cooperation, in cooperative communications. I very much share the vision that Ubli put in her talk, that communication, control, sensing, multi-agents are areas that have an enormous potential, and they're very fun problems to work with. And to study just a simple version of that problem, we looked at the relay channel in the dynamic setting. And we saw that indeed you can incentivize the users with a simple mechanism so that they can achieve, if they act strategically, the centralized solution of a problem that, is interested to the designer. Regarding our current work and our future work, we have two different directions, one which is more short-term and the other one that looks more like a long-term research problem. The first one is that we have already made an assumption here that the two users have purview of the entire system, x1t, x2t. And clearly, this is not a very practical scenario. We would like to lift that assumption and see what happens if every user knows only its own Q state. Incidentally, this is a very interesting problem even when you don't consider strategic users, even if you consider team players. That is a team of users that have a common goal, but they have different information constraints. That is, every user knows sort of a different thing about the system. Okay? We have solved the team problem, but we're working on the strategic case. The other one is much more difficult. We have assumed here, tacitly, that the cost functions rho of each user are common knowledge to the system. But really, if you think about it, my utility, my happiness function, is not something that I may be willing to share. Okay? So if you're not willing to share that, that is, if the shape of that function is private information, we get into this murky waters of what is called implementation theory in economics. And unfortunately, there are very few results in implementation theory when you have dynamic setup. So this is a more long-term, as I said, research goal. And with this, I will conclude my talk. Thank you very much.